All right, welcome to another deep dive. Today, we're really going deep into some pretty advanced math.
Yeah, definitely not for the faint of heart.
Absolutely not. But that's why you're here, right? To break it down.
That's the plan.
Our focus today is on a paper. Let me get the title right. It's Existence, Uniqueness, and Regularity for Elliptic p-Laplace Systems with Complex Coefficients.
What a mouthful. Yeah.
It is. And the authors are Wontae Kim and Matthias Vesberg.
Now, this paper, it really digs into some fascinating stuff. We're talking about extending what we know about p-Laplace equations, but in the world of complex numbers.
Right. So not just your everyday real numbers. This adds a whole other layer of complexity.
Exactly. And we're going to unpack how they managed to prove that solutions exist and under what conditions those solutions are unique. Then we'll look at the regularity of those solutions, how smooth they are.
And we can't forget the really interesting part, how these solutions change when the coefficients themselves depend on a complex parameter. That gets pretty wild.
It does. And you know, what's really cool is that this isn't just some abstract mathematical exercise. There are hints in the paper and in the field in general that this stuff could have real-world applications. Things like depot nets, a new kind of neural network, could potentially benefit from these findings.
So while it's heavy on the math, it's not just theory. It's pushing the boundaries of what we can do in a lot of different areas.
Okay, so enough with the intro. Let's get right into it. On page 1, the paper kicks off by laying out the central equation they're going to be tackling.
All right, let's see it.
Here it is. d to v plus the di phi q. Those are Mia. Do you recognize the structure if you're familiar with the classic p-Laplace equation? But big but, the coefficient a and the solution u, those can be complex numbers.
So right off the bat, we're not in Kansas anymore.
Not at all. All right, so let's break this equation down piece by piece. We have p, which is a real number, and it's got to be strictly between 1 and infinity.
Got it. P. 1, P. And this P, it controls how nonlinear the equation is, right?
Exactly. Then we've got or, another parameter, but this one's non-negative and lives between 0 and 1.
So or in 0, 1. Now, this or, it pops up a lot in regularization. Does it have a specific role here?
Good catch. The authors actually point out that most of their results still hold even when OI is 0, the exception being the differentiability part, which needs to be strictly positive. But for the most part, we could think of it as adding a little bit of, well, smoothness to the operator.
Interesting. Makes it a bit more well-behaved, I guess. Okay, what else have we got?
All right, so A, this is our domain, an open bounded subset of OI, the n-dimensional real space. And they specify that n has to be at least 2.
So we're in at least 2 dimensions, makes sense. What about the coefficient function, a?
Ah, A. This is where things get interesting. This function maps from our domain, A, into the complex numbers, C. And this is a key focus.
Complex coefficients, that's a big change from the real valued case. And U, our solution.
Right, so U goes from A into co, meaning it's a vector of n complex numbers, where n is at least 1.
Okay, a complex valued solution. Makes sense. And lastly, F.
F is our source term. It maps from A into coser. So basically a collection of m by n complex matrices.
Complex matrices, all right. We're really going all in on the complex numbers here. Now, you mentioned earlier that most results hold even when A is 0. What about those that don't?
Yeah, so the differentiability result, which we'll get to later, requires A to be strictly positive. It has to do with how the solution changes when we tweak a complex parameter in the coefficients.
Right, so A being positive kind of ensures that things behave nicely when we start playing around with those parameters.
And another important thing, since we're working with these complex valued solutions, we got to ditch the usual real inner product.
Ah, because it wouldn't quite work in the complex world.
Exactly. We need its complex cousin, denoted by AA. This one takes into account both the real and imaginary parts of the vectors.
So it's a more comprehensive inner product, I guess. We'll see its formal definition later, right?
Yeah, definition 2.2. But it's important to keep in mind from the get-go that we're working with this complex inner product throughout the paper.
Now, what about the source term F? What conditions do they put on that?
Well, these are pretty standard integrability condition. They assume F belongs to the Lebesgue space L sub P, where P is the Holder conjugate of P. So, 1P plus 1B are equal 1, 1.
Right. That ensures the integrals in the weak formulation behave nicely.
Exactly. So that covers the basics of the equation, but the real fun starts when we dig into the complex coefficient, AX.
Okay, what's so special about AX?
Well, they break it down into its real and imaginary parts.
Yep.
So AX is a x O sub x plus a sub x, where a sub and a sub are both real valued functions measurable, defined on our domain.
So we're separating the real and imaginary parts, and each of those gets to play a role.
Precisely. And to make sure things don't go haywire with this complex coefficient, they introduce these ellipticity conditions.
Ellipticity, right. We need that even in the real case. How does it work here?
They essentially say that the real part, a sub-sub, needs to be sufficiently dominant. So they have these constants, E and L, both positive, with E smaller than L, such that for almost every point in our domain is less than or equal to a sub-sub x, minus the absolute value of a sub-sub x, a and d a sub-sub x, plus the absolute value a of a sub-sub x is strictly less than L.
Okay, so we're bounding the real part both above and below, and we're controlling the imaginary part by keeping it within a certain range around the real part.
You got it. Now you might be wondering, why this focus on the real part being dominant? Well, it's all about stability.
So it's like the real part provides a solid foundation, and the imaginary part is allowed to fluctuate around it, but not too wildly.
Exactly. Now, these ellipticity conditions are key because they lead to some pretty important structural properties for the whole operator. Like they get this structure bound, which essentially says the operator doesn't grow too fast as the gradient increases.
That's good. We want things to stay under control.
Right. And on the flip side, we also have a coercivity property. This one relates to the real part of the operator and provides a lower bound.
Coercivity is essential for proving stuff like existence of solutions, isn't it?
Absolutely. But here's the kicker, monotonicity, which is super important for existence and uniqueness. It gets a lot trickier in this complex world.
Trickier how?
Well, it really depends on the relationship between a sub-sub and a sub-sub. The authors point out that they need an extra condition to guarantee monotonicity, something like T is sub x, a C case is x, where C and C are positive constants that pop up later in the structural lemmas.
So again, we see this interplay between the real and imaginary parts being super important.
Exactly. Now, it's under these very specific conditions that they're able to show that a weak solution exists for the Dirichlet problem. And they do this by extending the theory of monotone operators to the complex realm.
Monotone operators, that's a whole other deep dive in itself.
It is. But the key takeaway here is that they're pushing the boundaries of the theory to deal with these complex valued p-Laplace equations. They even mention this as a novel contribution, as far as they know.
That's pretty cool, being at the forefront of mathematical research like that.
Right. And they don't stop at existence. They also show that these solutions are unique. And they achieve this through an energy estimate, which gives us a bound on how much the solutions can differ.
Makes sense. Uniqueness is important. We don't want multiple solutions floating around causing confusion.
Exactly. So we've got existence and uniqueness, but the story doesn't end there. They also delve into the regularity of the solutions, how smooth they are.
Right. Smoothness matters. It tells us how well behaved the solutions are.
Absolutely. And they show that they get the classic Schroeder estimate. Now, this basically means they can bound how wiggly the solution is based on how wiggly the source term and coefficients are.
So if our source term and coefficients are nice and smooth, our solution will be too.
Precisely. And the fact that they get this Schroeder estimate for Holder continuous coefficients and source term, that's a big deal. It tells us a lot about the behavior of these solutions.
Okay, so we've got existence, uniqueness, and now some understanding of the smoothness of the solutions. What's left?
The grand finale. They look at how the solution changes when the coefficients themselves depend on a complex parameter.
Right, that's the part you were excited about earlier. How do they even approach that?
They get this differentiability result for the map that takes the complex parameter to the solution, and they focus on line segments within the domain of the parameter.
So they're looking at how the solution changes along specific directions in the complex plane.
Precisely. And they even tie it back to the linear case, where p is 2. Turns out, similar questions about complex differentiability have been studied there, especially in the context of series expansions and depot nets.
Depot nets again, so this really does connect to a lot of different areas.
It does. It highlights the potential impact of their work, even beyond the immediate mathematical context. So that's the big picture. They're really laying the groundwork for a deep understanding of these complex p-Laplace systems. Okay, that's a great overview. Now let's go back to page 2 and unpack those preliminary definitions. They're going to be crucial for understanding the rest of the paper.
Absolutely. So definition 2.1 starts off by defining the real vector space. Essentially, it's a collection of n tuples, where each tuple is a vector in Rye.
Okay, so we're talking about vectors of vectors, basically.
Right. And then they define the inner product and the norm for this space. The inner product is just the sum of the usual Euclidean inner products of the corresponding vector components. And the norm is the square root of the inner product of a vector with itself.
Standard stuff so far.
Yep. But then definition 2.2 takes us into the complex realm. It defines K, the space of complex matrices, by saying that each element has a real part and an imaginary part, both belonging to the real space raw we just defined. Okay, so we're building the complex space from the real one.
Exactly. And then they define scalar multiplication and, most importantly, the complex inner product for this space. This is key because it tells us how to measure overlap between complex vectors.
Right, because the usual real inner product wouldn't quite cut it here. So what does this complex inner product look like?
Well, it's a bit more involved. It involves the real and imaginary parts of both vectors. They take the Euclidean inner product of the real parts, then the Euclidean inner product of the imaginary parts, and then they combine those with some clever use of the imaginary unit. It's like a more intricate dance between the real and imaginary components.
Sounds like it. And they also define the norm for this complex space, right?
Yeah, the norm is defined in terms of the norms of the real and imaginary parts in the real space. It's basically the square root of the sum of the norms of those parts.
So it's taking into account both the real and imaginary magnitudes.
Precisely. Now, definition 2.3 is where they introduce this really neat trick. They define two new notations, F, read as double F, and QF. These essentially let us represent a complex matrix as a real matrix of twice the dimension.
Wait, how does that work?
So for F, they basically stack the real imaginary parts of the vector components on top of each other. And for QF, they do a little rearranging and sign flipping with the real and imaginary parts. It seems a bit arbitrary at first, but it turns out to be super useful.
Okay, why is this useful?
Because it lets them connect the complex inner product to the real inner product. They show that the complex inner product of two complex matrices can be written as a combination of the real inner products of their F and QF representations.
Ah, so it's like a bridge between the complex and real worlds.
Exactly. And they also point out this crucial norm equivalence. The norm of a complex matrix is the same whether we calculate it in the complex space or using its F or QF representation in the real space.
So we have this freedom to switch back and forth between the complex and real representations without messing up the magnitudes.
Exactly. Now, definition 2.4 is a quickie. It just reminds us how to take the real and imaginary parts of a complex number, a scalar.
Simple enough.
Right. Definition 2.5 is another reminder, this time, of the Lebesgue space L sub sup rho. This is the space where the source term usually lives.
Familiar territory.
Yep. Then comes definition 2.6, which defines the complex Sobolev space 1 of sub 1 sub su. This is the space where our solutions will live. It's basically the space of functions whose real and imaginary parts, along with their gradients, have finite L sub sup norms.
Okay, so this is the natural space for studying solutions to these complex p-Laplace equations with Dirichlet boundary conditions.
Precisely. And finally, definition 2.7 introduces a couple more notations, U and a chu, which are similar to F but for the solution U. They basically stack the real and imaginary parts of A and its gradient.
More notational convenience to make the expressions easier to handle.
Yeah, exactly. So with all these definitions in place, we're finally ready to tackle the complex p-Laplace system head on.
Let's do it. Section 3, page 4, brings us to the formal introduction of this complex beast.
They start by reminding us how the coefficient AX is split into its real and imaginary parts. AX equals a sub x plus a sub x, and that both a sub and a sub are bounded and measurable.
Okay, still making sure those coefficients are well behaved.
Yep. And then they restate the crucial ellipticity conditions labeled 5. Again, these are super important because they control the relationship between the real and imaginary parts of the coefficient.
Right, ensuring the real part stays dominant, keeping things stable.
Exactly. Now, definition 3.1 is the formal definition of what it means to be a weak solution to this complex p-Laplace equation. They basically turn the differential equation into an integral equation that has to hold for all test functions in the complex Sobolev space. W1, sub.
Weak formulation, classic technique in PDE theory.
It is. It's often easier to work with than the original differential equation, especially when we're dealing with solutions that might not be super smooth in the classical sense.
Okay, so we've got the problem set up. We know what a solution looks like. Now it's time for the heavy lifting write-up.
You got it. Section 4, starting on page 5, is all about the structure. Lemmas. These are not theorems about existence or uniqueness, but they're like the tools we need to build those proofs.
Okay, so they lay the groundwork for the main results.
Exactly. Lemma 4.1 is the first one, It gives us an expansion of the complex inner product of a particular expression. They write it in terms of the F and QF representations that we saw earlier, and this lets them connect it back to the real inner product.
That bridge between the complex and real world again seems like a recurring theme.
It is. Now, lemma 4.2, this one is about coercivity. It gives us a lower bound on a certain expression that involves the real part of the operator.
Coercivity, good stuff. We need that for existence proofs.
Right. Then we have lemma 4.3, which gives us a bound on the difference between the operators themselves. This essentially tells us that the operator is Lipschitz continuous in a certain sense, meaning it doesn't jump around wildly.
Okay, that makes sense. We want things to be relatively continuous.
Right. And finally, lemma 4.4 gives us an equivalence of norms involving the difference of the operators raised to different powers.
So we can swap between different representations without messing things up too much.
Exactly. These four lemmas are like the foundation on which the rest of the paper is built. They're used over and over again in the proofs.
Okay, so let's get to those proofs. Section 5, page 6, is where the existence and uniqueness results live.
Right. They start by introducing a new condition, labeled 7. It's an additional constraint on the relationship between the real and imaginary parts of the coefficient.
So on top of the ellipticity conditions, we have this extra condition as well.
Yep. It essentially ensures that the real part of the coefficient stays sufficiently dominant, which is crucial for things like monotonicity.
I'm sensing a pattern here. The balance between the real and imaginary parts is everything.
You got it. Now, they make an interesting observation. When p is 2, which is the linear case, this new condition, 7, just reduces to the first ellipticity condition.
So it's like this extra condition is only really needed for the nonlinear case.
Exactly. They even mention that they don't know the optimal values for the constants in this new condition for general p.
Okay, so there's still some mystery there, room for further exploration.
Definitely. Then definition 5.1 formally defines the class E of coefficient functions that satisfy all the required conditions. The splitting into real and imaginary parts, the ellipticity conditions, and this new condition.
7. So this is the club of well-behaved coefficients that we're allowed to work with.
Precisely. And with that setup, they jump right into theorem 5.2, which is the uniqueness result. The proof is pretty elegant. They assume you have two different solutions and then show that their difference has to be 0.
Classic uniqueness proof strategies show that any two solutions must be the same.
Right. And they do this by using the structure lemmas, the ellipticity conditions, and that new condition, 7. They essentially show that the gradients of the two solutions have to be the same, which then implies the solutions themselves must be the same.
So uniqueness is locked down. What about existence?
That's theorem 5.3, which deals with the case where the solution is 0 on the boundary of the domain. The proof is quite a bit more involved. It uses monotone operator theory and some pretty slick compactness arguments.
Monotone operators, again, powerful stuff.
They are. So the basic idea is to first approximate the solution in finite dimensional subspaces, kind of like building it up piece by piece. Then they use the energy estimates we talked about earlier to show that this sequence of approximations has a limit.
And that limit is our solution.
Exactly. But they had to carefully show that this limit actually satisfies the original equation. That involves taking limits of integrals and using all those structure lemmas and conditions we talked about.
Sounds pretty intense, but they managed to pull it off.
They do. And then corollary 5.6 extends this existence result to the case where the solution doesn't have to be 0 on the boundary. They basically transform the problem into one with 0 boundary conditions by subtracting off a function that takes care of the boundary values.
Clever.
It is. So to sum up section 5, they've nailed down both uniqueness and existence of solutions. And they did it by carefully using monotone operator theory, approximation techniques, and some smart manipulation of inequalities.
A tour de force of mathematical analysis. Now, once you have existence and uniqueness, the next big question is regularity. How smooth are these solutions? That's section 6, right?
Exactly. Starting on page 12, they dive into the gradient holder continuity of the solutions. This is all about understanding how much the gradient of the solution can change over small distances.
So if the gradient is Holder continuous, it means it can't jump around too wildly.
Precisely. Now, theorem 6.1 is the main regularity result. It says that if the coefficient is Holder continuous and belongs to that special class E, and if the source term is also Holder continuous, then the gradient of the solution is locally Holder continuous.
Okay, so the smoothness of the solution is inherited from the smoothness of the coefficient and the source term.
Exactly. And they even get an explicit bound on how much the gradient can change.
That's always nice to have a quantitative estimate.
Yeah, it is. Now, the proof of Theorem 6.1 is pretty involved. But the basic strategy is to leverage known results for the real-valued p-Laplace equation.
Using what we know about the real case to tackle the complex case.
Right. So they first look at a simplified model problem where the source term is 0 and the coefficient is just 1. They show that this model problem can be transformed into a real-valued p-Laplace equation.
So they bridge the gap between the complex and real worlds again.
Exactly. And for this real-valued equation, they can use existing regularity results, specifically Theorem 6.2 from another paper, which guarantees that the gradient of the solution to this model problem is Holder continuous.
Okay, so they have Holder continuity for the simplified model problem. Now they need to extend that to the general case.
Right. And to do that, they prove a series of lemmas. Lemma 6.3 provides an energy estimate for the solution to the model problem. It basically relates the gradient of the solution to the model problem to the gradient of the solution to the original problem.
So it's like a bridge between the two.
Exactly. Then Lemma 6.4 gives us an estimate on the difference between the gradients of the solutions to the original problem and the model problem.
Okay, so we're controlling how much those gradients can differ.
Precisely. Then comes Lemma 6.5, a growth lemma. This one is a bit technical, but essentially it says that the integral of the gradient over a small ball can't be too much bigger than the integral over a larger ball.
So it's controlling how fast the gradient can grow as we move out from a point.
Right. With these lemmas in place, they can finally prove Theorem 6.1. It involves using the triangle inequality to relate the gradient of the solution to the original problem to the gradient of the solution to the model problem, and then using all the estimates they've derived.
These sound like a lot of careful bookkeeping.
It is. But the key takeaway is that they managed to show that the gradient of the solution to the complex p-Laplace equation is Holder continuous, inheriting the smoothness from the coefficient and the source term.
Okay, so we've tackled existence, uniqueness, and regularity. What's left?
The final challenge, section 7, page 19. This is where they look at what happens when the coefficient itself depends on a complex parameter.
Right, so we're adding another layer of complexity. The coefficient is no longer fixed, it's changing with this parameter.
Exactly. Now, Theorem 7.1 is a global Holder continuity result for rectangular domains. It's basically an extension of Theorem 6.1 to the case where the domain is a rectangle.
Rectangular domains are nice, they often simplify things.
They do. But the real star of the show is Theorem 7.2. This one is about the differentiability of the solution map. It tells us how the solution changes when we wiggle that complex parameter in the coefficient.
Okay, that's getting into some pretty advanced territory.
It is. And the proof is, well, let's just say it's not for the faint of heart. It involves using all the tools they've developed so far. Energy estimates, compactness arguments, weak convergence, strong convergence, you name it.
Sounds like a mathematical symphony.
It is. But the payoff is huge. They show that under certain conditions, the solution map is differentiable with respect to that complex parameter.
That's pretty remarkable considering all the complexity involved.
It is, and it opens up a whole world of possibilities for applications, like in those deponents we talked about earlier.
So to wrap things up, this paper is a deep dive into the world of complex p-Laplace equations. They establish existence, uniqueness, regularity, and even differentiability with respect to a parameter. It's a real testament to the power of mathematical analysis.
Absolutely. And they do it all with such rigor and precision. It's a beautiful piece of work.
It is. And for those who want to explore further, we highly recommend reading the full paper and digging into the references.
There's so much more to discover in this fascinating area of mathematics.
Thanks for joining us on this deep dive, and we'll see you on the next one.
Until then, keep exploring. All right, so we're diving deep today into some pretty advanced math.
Yeah, definitely.
We're going to try to pull out the really important stuff, you know.
Exactly, sort of the shortcut to understanding all the details of this paper.
Exactly, all the equations, the proofs.
All that good stuff.
Yeah, you know, assume our listeners are already pretty familiar with math.
Oh yeah, we're not holding back on the technical stuff.
Nope, this is existence, uniqueness, and regularity for elliptic p-Laplace systems with complex coefficients, right?
By Wontae Kim and Matthias Vestberg, that's the one.
Okay, so first off, we're looking at how they take the real-valued p-Laplace theory and
extend it to complex valued functions.
yeah, which is
not a simple thing to do.
No, not at all. And the way they change things is pretty interesting.
Yeah, and there's a lot to unpack there.
Okay, and then we've got the conditions for existence and uniqueness of solutions to the Dirichlet problem.
Right, and figuring out when those solutions are unique, that's important.
Yeah, got to make sure there's only one solution, right?
Absolutely, and the real and imaginary components play a huge role there.
Okay, so after that, we're on to the Schroeder estimates, which is...
That's the key to understanding the regularity, the smoothness of the solutions.
Smoothness.
Yeah, and we'll look closely at how the Holder continuity of the coefficients and the source terms affect that smoothness.
All right, and finally...
Finally, we look at what happens when the coefficients themselves aren't fixed, but depend on a complex parameter.
Oh, interesting.
Yeah, and that leads to a result about the differentiability of the solution map.
With respect to that parameter, right?
Exactly.
Okay, so big picture stuff.
Yeah, this research isn't just some abstract thing. It connects to all sorts of areas in math.
And could even have applications in stuff like depot nets, right?
Yeah, like the authors mentioned depot nets, which are these new types of neural networks that are designed to learn operators.
So advanced math, but
with real-world implication.
Gotcha. Okay, let's jump into the paper then, starting on page 1 with the introduction.
Sounds good.
So they start by setting the stage with the main equation they're looking at.
Right, the equation that they're going to be working with the whole time. It's negative divergence of a times the quantity epsilon squared plus the magnitude of the gradient of u squared, all raised to the power of p minus 2 over 2 times the gradient of u equals negative divergence of f in omega.
Okay, there's a lot there.
Yeah, but if you're familiar with the classic p-Laplace equation...
It looks kind of familiar.
Yeah, the structure's similar, but the big difference here, the thing that makes this paper so interesting, is that the coefficient a and the solution u, they can be complex numbers.
Okay, so that's where it gets tricky.
That's where it diverges from the real-valued theory.
All right, so let's break down what all those symbols actually mean.
Sure.
So p is a real number.
Between 1 and infinity, not including 1 or infinity.
Right, so p is an element of the open interval 1 to infinity.
Exactly, and that p, that exponent, that's what controls how nonlinear the equation is.
Okay, and then there's epsilon.
Epsilon, a non-negative parameter between 0 and 1 inclusive.
So epsilon is an element of the closed interval from 0 to 1.
Right, and you see epsilon a lot in regularization techniques.
And they mentioned that a lot of their results hold even when epsilon is 0.
Yeah, which means it simplifies to the standard p-Laplace operator.
Got it.
Okay, and then we have omega, which is the domain.
Open and bounded subset of r to the n being greater than or equal to 2.
Right, so it's an n-dimensional real space, and n has to be at least 2.
Okay.
Now, for the coefficient function, a, it maps from omega into the complex numbers, c.
And complex a is like the whole focus of the paper, right?
It's a big part of it, yeah.
And the solution, u, goes from omega to c to the n.
So it's a vector with n complex numbers, where n is some positive integer, at least 1.
Okay, and then there's f, the source term.
Which goes from omega to c to the n by n.
So it's like a collection of n by n matrices with complex number entries.
Exactly.
So just to make sure I'm getting this, most of their results still work even when epsilon equals 0.
For the most part, yeah.
Except for the differentiability result that depends on the complex parameter in the coefficients.
Right, that's in the later sections of the paper, and they need epsilon to be positive for that one.
Okay, so epsilon being positive adds a little bit of smoothness, makes things a little less degenerate.
Exactly.
Okay, and then because u is complex valued, the usual real inner product has to be replaced.
With its complex counterpart denoted by those angled brackets, you know.
Like the complex inner product.
Yeah, we'll see the exact definition later on in definition 2.2, but it's a crucial concept.
Okay, so that complex inner product takes both the real and imaginary parts of the vectors into account.
Exactly.
Now, for the source term, f, they use a standard integrability condition.
Like you'd see in the real valued setting, yeah.
So they assume that f is in the Lebesgue space, L to the power of p prime of omega semicolon c to the n by n.
Where p prime is the Holder conjugate of p.
Which means
1 over p plus 1 over p prime equals 1.
Okay, so that ensures the integrals in the weak formulation are well defined.
And finite.
Okay, now let's get into the structure of x. the complex coefficient.
That's where things get really interesting.
Yeah, that's where the complexity comes in.
They break down a of x into its real and imaginary parts.
So a of x equals a sub r of x plus I times a sub I of x.
Where a sub r and a sub I are real valued functions.
And measurable defined on omega.
Right, so we can look at the real and imaginary components separately.
Okay, and for ellipticity, which is key to make sure the problem is well posed, we need to consider both a sub r and a sub I.
Yep, got to extend that concept from the real valued case to the complex setting.
So they have these ellipticity conditions.
They assume there are positive constants nu and L, where nu is less than L.
And such that, for almost every x in omega, nu is less than or equal to a sub r of x minus the absolute value of a sub I of x, and a sub I of x plus the absolute value of a sub I of x is strictly less than L.
Exactly, and remember, a sub I of x, the imaginary part, can be negative.
Right, so we need those absolute values.
Those absolute values are key.
Okay, so these conditions are really important.
They make sure the real part of the coefficient is kind of dominant, which keeps things stable.
Nu being positive ensures the operator is invertible or coercive.
Right, and L being finite prevents it from becoming degenerate.
Okay, so that's what makes these complex systems well-behaved.
Yeah, it's what allows us to even start looking for solutions.
All right, so these ellipticity conditions lead to some important structural properties.
Like the structure bound,
which is the absolute value of x times the quantity epsilon squared plus the magnitude of epsilon squared, all raised to the power of p minus 2 over 2 times the complex inner product of xc with itself is less than or equal to 2 to the power of p times the quantity epsilon to the p plus the magnitude of x of the p.
right? Xi is an element of c to the n by n, representing a potential gradient.
So this bound tells us the operator doesn't grow too quickly as the gradient gets bigger.
Which is often needed to prove boundedness of solutions or approximations, yeah.
Okay, and then there's the coercivity property.
Which is about the real part of the operator.
So the real part of x times the quantity epsilon squared plus the magnitude of x squared, all raised to the power of p minus 2 over 2 times the complex inner product of x squared with itself equals a sub r of x times the quantity epsilon squared plus the magnitude of sig squared, all raised to the power of p minus 2 over 2 times the magnitude of x squared. And this is greater than or equal to nu times the quantity epsilon squared plus the magnitude of sec squared, all raised to the power of p minus 2 over 2 times the magnitude of sec squared.
Exactly. And coercivity, that's a fundamental concept in PDEs.
Right. It gives a lower bound on the energy functional, which is often needed to prove the existence of solutions.
Using variational methods or monotone operator theory.
Okay, now monotonicity, which is important for existence and uniqueness, gets a lot more complicated here.
Because we're in the complex setting, yeah.
The authors say that monotonicity of the operator depends a lot on the relationship between a sub r and a sub I.
They need an extra condition to ensure monotonicity.
Which is c sub 1 times a sub r of x minus c sub 2 times the absolute value of a sub I of x is greater than nu.
Where c sub 1 and c sub 2 are positive constants that will show up later in lemma 4.2 and lemma 4.3.
This condition makes sure the real and imaginary parts are balanced in a way that gives us monotonicity.
And that's key for existence and uniqueness.
So with these conditions, the ellipticity conditions and this extra condition, they can prove the existence of a weak solution.
And they do it by extending monotone operator theory from the real valued case to the complex valued case.
Which they say is a brand new contribution.
To the best of their knowledge at the time, yeah.
That connection between the real and imaginary parts, that's what determines if a solution even exists.
It's really important, yeah.
Okay, and they also have a uniqueness result.
Which comes from an energy estimate.
Energy estimates give bounds on the norms of the solutions.
And you can use those to prove uniqueness by showing that the difference of two solutions has zero energy.
Meaning they're the same solution.
Exactly.
Okay, so they move on to talk about the regularity of the solutions.
They get a Schotter estimate.
Schotter estimates give bounds on the Holder norm of the second derivatives, or the gradient, in terms of the Holder norm of the right-hand side and the coefficients.
Right. And Holder continuity tells us how smooth the function is, how controlled its rate of change is.
So they prove these estimates for Holder continuous coefficients and source term.
Which tells us how smooth the solutions are.
Okay, and then they look at how the solution depends on a complex parameter in the coefficient function.
They have a differentiability result for the map that takes the parameter to the solution.
And they look at this differentiability along line segments.
For epsilon, greater than 0, and rectangular domains.
Okay, so that's important for understanding how sensitive the solutions are to changes in the parameters.
Exactly.
And they connect this back to the linear case where p equals 2.
Where similar questions about complex differentiability have been studied.
Especially for series expansions of solutions and their applications to things like deep and eds.
Right, so their work on nonlinear complex PDEs has broader relevance.
Okay, that gives us a good overview of the problem and the results.
Now let's dive into the nitty-gritty, starting with the definitions in Section 2.
Page 2, here we go.
These definitions are super important. They lay the foundation for everything that follows.
Right, we need to understand these to understand the rest of the paper.
Absolutely.
So definition 2.1 starts with defining the real vector space R to the n by n.
Each element in this space is like an n-tuple of vectors in R to the n.
Okay, and they extend the Euclidean inner product to this space.
So for f and g in R to the n by n, their inner product is f dot dg, which equals the sum from j equals 1 to n of f sub j dot g sub j, where those dots on the right-hand side are the usual dot product in R to the n.
Okay, so we're just adding up the dot products of the corresponding components.
Exactly.
And the norm in R to the n by n, the magnitude of f, is just the square root of f dot f.
Right, standard definition of the norm.
Definition 2.2 then extends this to the complex setting.
To the space C to the n by n.
So an element f in C to the n by n has a real part, f sub r, and an imaginary part, f sub I.
Both of which are elements of R to the n by n.
And f is written as f sub r plus I times f sub I.
Where I is the imaginary unit, of course.
Right, and scalar multiplication by a real number c is defined as c times f equals c times f sub r plus I times c times f sub I.
Straightforward extension of scalar multiplication.
Okay, and now for the key definition, the complex inner product.
For f and g and c to the n by n.
So the complex inner product of f and g is the sum from j equals 1 to n of the quantity f sub rj dot g sub rj plus f sub ij dot c sub j plus f sub ij dot g sub ij plus, it's the sum over the n components.
For each component, we have the dot product of the real parts and the dot product of the imaginary parts.
And those contribute to the real part of the complex inner product.
Right, and the imaginary part comes from that term with the I in front.
Which mixes the real part of one with the imaginary part of the other.
It's a more nuanced way of measuring the relationship between complex vectors.
Okay, and then the norm of f in C to the n by n, the magnitude of f, is defined as the square root of the quantity, the magnitude of f sub r squared plus the magnitude of f sub I squared.
Using the norms from R to the n by n.
So it's measuring the overall magnitude of f by considering both its real and imaginary parts.
Right.
Definition 2.3 introduces this double f notation.
Double f.
So for f in C to the n by n, double f is a vector in R to the 2n by n.
Where you stack the real and imaginary parts of the n vector components.
So double f equals f sub r1 and so on, up to f sub rn, comma, f sub i1 and so on, up to f sub in.
So we're taking a complex vector of dimension n and turning it into a real vector of dimension 2n.
And then there's qf, which is negative f sub i1 and so on, up to negative f sub in, comma, f sub r1 and so on, up to f sub rn.
So it's like a rearrangement and sign change of the components.
These seem kind of arbitrary, but
they're super useful, trust me.
Yeah.
So the key insight here is the relationship between the complex inner product and the real inner product.
So the complex inner product of f and g is equal to double f dot double g plus I times double f dot qg.
Where the dot on the right-hand side is the usual dot product in R to the 2n by n.
So we can use what we know about the real inner product to deal with complex quantities.
Exactly.
And there's also a norm equivalence. The magnitude of double f equals the magnitude of qf, which equals the magnitude of f.
So the norm of f in C to the n by n is the same as the norm of its representations in the doubled real space.
Okay, and definition 2.4 is just about the real and imaginary parts of a complex number.
Simple stuff.
Definition 2.5 reminds us about the Lebesgue space L to the p of omega semicolon r to the n by n.
All the measurable maps from omega to r to the n by n with finite integral of the p-Laplace power of their norm.
Standard space for the source term in real-valued p-Laplace problems.
Right.
Definition 2.6 extends the Sobolev space W to the 1p sub 0 to the complex setting.
Giving us w to the 1 p sub 0 of omega semicolon c to the n.
So a function is in this space if both u and its gradient have finite L to the p norms.
We break down u into its real and imaginary parts, u sub r and u sub I.
Both of which have to be in the real Sobolev space. W to the 1 p sub 0 of omega semicolon r to the n.
Same for the gradient u sub r plus I times u sub I.
And the sub-zero means the function has zero boundary values.
This is the natural space for Dirichlet boundary value problems.
Okay, and finally, definition 2.7 introduces some more shorthand.
For u and w to the 1 p sub 0 of omega semicolon c to the n.
They define hat u as a vector in the real space by stacking the real and imaginary components of u.
So hat u equals u sub r1 and so on, up to u sub rm, comma, u sub i1 and so on, up to u sub in.
Just like double F.
Right, and they define hat u similarly.
And then Q and Hisho, analogous to QF.
These will make the equations and proofs look a lot cleaner.
Okay, so those are all the basic definitions.
Now I can really get into the meat of the paper, starting with section 3.
Which is about the complex-valued p-Laplace system.
On page 4,
they restate the form of the complex coefficient a of x as a sub r of x plus I times a sub I of x.
And they remind us that a sub r and a sub I are bounded, measurable, real-valued functions on omega.
And they restate the ellipticity conditions, nu less than or equal to a sub r of x minus the absolute value of a sub I of x, and a sub r of x plus the absolute value of a sub I of x is strictly less than L.
Where nu and L are positive constants with nu strictly less than L.
These conditions are super important.
Yeah, they make sure the problem is well behaved.
And they generalize the usual ellipticity condition for real valued coefficients.
Exactly.
Okay, and then there's definition 3.1, which defines what it means for a function u in w to the 1p of omega semicolon c to the n to be a weak solution.
Should the PDE.
Right. Negative divergence of x times the quantity epsilon squared plus the magnitude of the gradient of u squared, all raised to the power of p minus 2 over 2 times the gradient of u equals negative divergence of f in omega.
They rewrite this as an integral equation.
So for every test function phi in w to the 1, p sub 0 of omega semicolon c to the n, the integral over omega of x times the quantity epsilon squared plus the magnitude of the gradient of u squared, all raised to the power of p minus 2 over 2 times the complex inner product of the gradient of u, and the gradient of phi dx equals the integral over omega of the complex inner product of f and the gradient of phi dx.
This weak formulation is standard for PDEs, especially when we're looking for solutions that might not be differentiable in the classical sense.
Right, so instead of requiring the equation to hold at every point, we require to hold in an integrated sense.
Against a bunch of test functions.
And we use test functions in w to the 1, p sub 0 of omega semicolon c to the n, because we're dealing with Dirichlet boundary conditions.
Exactly.
Okay, so now that we've set up the problem with all the definitions in the main equation, we move on to section 4.
Where we have a bunch of structure lemmas.
These lemmas are like the tools we need to prove the main theorems.
They establish important inequalities that come from the assumptions we've made.
About the complex coefficient and the norms and inner products.
Starting on page 5.
So lemma 4.1 gives an expansion of the complex inner product term. The complex inner product of the quantity epsilon squared plus the magnitude of f squared, all raised to the power of p minus 2 over 2 times f minus the quantity epsilon squared, plus the magnitude of g squared, all raised to the power of p minus 2 over 2 times g, comma, f minus g.
This expansion is in terms of double f, double G, QF, and QG.
We do those real space representations we defined earlier.
And it uses the real inner product in R to the 2n by n.
This lemma lets us connect the complex inner product back to the real inner product,
where we have more tools and inequalities to work with.
Okay, lemma 4.2 gives a coercivity condition for the real part of an expression.
It says there's a positive constant c sub 1, which might depend on p, such that c sub 1 times the quantity epsilon squared plus the magnitude of f squared plus the magnitude of g squared, all raised to the power of p minus 2 over 2 times the magnitude of f minus g squared, is less than or equal to the quantity epsilon squared plus the magnitude of double f squared, all raised to the power of p minus 2 over 2 times double f minus the quantity epsilon squared plus the magnitude of double g squared, all raised to the power of t minus 2 over 2 times double g, close quantity dot product with double f minus double g.
Where the dot product is in R to the 2n by n.
This gives a lower bound related to the difference between f and g for an expression involving the difference of the operators acting on their real space representations.
Okay, and lemma 4.3 bounds the magnitude of the difference of the operators.
It says there's another positive constant c sub 2, maybe depending on p, such that the magnitude of the quantity epsilon squared plus the magnitude of f squared, all raised to the power of p minus 2 over 2 times f minus the quantity epsilon squared, plus the magnitude of g squared, all raised to the power of p minus 2 over 2 times g, is less than or equal to c sub 2 times the quantity epsilon squared plus the magnitude of f squared plus the magnitude of g squared, all raised to the power of p minus 2 over 2 times the magnitude of f minus g.
Where the norms are the complex norms in c to the n by n.
This basically says the operator is Lipschitz continuous in a weighted sense,
Which is useful when dealing with nonlinear operators.
for proving continuity or applying fixed-point theorems.
Okay, and lastly, lemma 4.4 gives a norm equivalence for the difference of related operators.
There's a constant c greater than 0, depending on p, such that c inverse times the magnitude of the quantity epsilon squared plus the magnitude of f squared, all raised to the power of p minus 4 over 4 times f minus the quantity epsilon squared plus the magnitude of g squared, all raised to the power of p minus 4 over 4 times g, close quantity squared is less than or equal to the quantity epsilon squared plus the magnitude of f squared plus the magnitude of g squared, all raised to the power of p minus 2 over 2 times the magnitude of f minus g squared, which is less than or equal to c times the magnitude of the quantity epsilon squared plus the magnitude of f squared, all raised to the power of p minus 4 over 4 times f minus the quantity epsilon squared plus the magnitude of g squared, all raised to the power of p minus 4 over 4 times g, close quantity squared.
Again, all norms are in c to the n by n,
This relates the difference of the operators raised to different powers.
which can be helpful for estimations.
These 4 lemmas are the building blocks for the rest of the paper.
Yeah, they're used over and over again in the proofs for existence, uniqueness, and regularity.
They capture the behavior of the complex p-Laplace operator and the relationships between different quantities,
Okay, on to section 5.
where they talk about existence and uniqueness of weak solutions.
Page 6.
They start by adding another condition, labeled as 7,
Which is c sub 1 times a sub r of x minus c sub, 2 times the absolute value of a sub I of x is greater than nu.
where c sub 1 and c sub 2 are the constants from lemmas 4.2 and 4.3.
And nu is the lower bound from the ellipticity condition.
This condition puts a further restriction on the relative size of the imaginary part of the coefficient compared to the real part,
It ensures the real part of the operator, which provides stability, stays dominant.
over the imaginary part, which could introduce oscillations.
They point out that when p equals 2, which is the linear case, c sub 1 and c sub 2 are both 1.
So condition 7 simplifies to a sub r of x minus the absolute value of a sub I of x is greater than nu.
Which is just the first part of the ellipticity condition.
So this extra condition is really only needed for the nonlinear case where p is not equal to 2,
Okay, and then definition 5.1 defines the class E of omega.
which is the set of coefficient functions a that satisfy all 3 conditions.
The representation is a complex function, the ellipticity conditions, and this new condition 7.
These are the coefficients for which the existence and uniqueness results hold.
Okay, theorem 5.2 is the uniqueness result.
The proof starts by assuming we have 2 weak solutions, u and w.
In the defined space, g plus w to the 1, p sub 0 of omega semicolon c to the n, where g is some boundary value.
They look at the difference, v equals u minus w, which is in w to the 1, p sub 0 of omega semicolon c to the n,
Then they use v as a test function in the weak formulations for u and w.
and subtract those 2 formulations to get an equation involving the difference of the operators evaluated at u and w tested against w.
And then they take the real part of this equation.
Using lemma 4.1 to expand the complex inner product,
And lemmas 4.2 and 4.3, along with condition 7, to get an inequality.
which eventually leads to 0 being greater than or equal to the integral over omega of nu times the quantity epsilon squared plus the magnitude of u squared plus the magnitude of u squared, all raised to the power of p minus 2 over 2 times the magnitude of u minus u squared dx.
Since nu is positive, and that other term is non-negative, the only way for this inequality to hold is if u minus u sub u is 0 almost everywhere.
Which means the gradients are the same almost everywhere.
And since they have the same boundary conditions, u and w must be the same almost everywhere.
So the solution is unique.
Okay, theorem 5.3 is the existence result.
For vanishing boundary data, meaning u is in w to the 1, p sub 0 of omega semicolon c to the n,
They adapt monotone operator theory to prove this.
which is a powerful tool for proving existence in nonlinear PDEs.
So first they note that w to the 1 p sub 0 of omega semicolon c to the n is separable.
Meaning it has a countable dense subset.
They call this subset curly brace phi sub j curly brace sub j in n.
And for each m, they consider the finite dimensional subspace w sub m spanned by the first m elements of this subset.
For each z equals z sub 1 and so on, up to z sub m and c to the m, they define u of z in w sub m as the linear combination u of z equals the sum from j equals 1 to m of z sub j times phi sub j.
And they define a map G from C to the M to C to the M, where each component G sub j of Z is the integral over omega of x times the quantity epsilon squared plus the magnitude of the gradient of z squared, all raised to the power of p minus 2 over 2 times the complex inner product of the gradient of z and the gradient of phi sub j dx minus the integral over omega of the complex inner product of f and the gradient of phi sub j dx.
This is related to the weak formulation.
Finding a z sub 0 where g of z sub 0 equals 0 is the same as finding a u of z sub 0 in w sub m that satisfies the weak formulation when tested against the basis functions.
They then look at the real part of the complex inner product of g of z with z.
And use the ellipticity condition and Holder's inequality to show that for large enough z, the real part of this inner product is non-negative.
And that allows them to use lemma 5.5, which is a variant of a fixed point theorem.
This lemma says that if we have a continuous map G from C to the M to C to the M, and there's a radius rho where the real part of the inner product of G with Z is non-negative for all Z on the boundary of the ball of radius rho, then there's a point Z sub 0 inside the ball where G of Z sub 0 equals 0.
Okay, so using this lemma, they find a Z sub M in C to the M where G of Z sub M equals 0.
Which gives them a function U sub M and W sub M that satisfies a finite dimensional approximation of the weak formulation.
And they get an energy estimate for U sub M,
which gives a uniform bound on the L to the P norm of the gradient of U sub M, independent of M.
This bound is key for the next step, which uses compactness.
The uniform bound lets them use the Banach-Alaoglu theorem to find a subsequence of Y Zal sub M that converges weakly in L to the P to some U sub M.
And since the embedding of W to the 1, P sub 0 into L to the P is compact, the corresponding subsequence of U sub M converges strongly in L to the P to some U.
And U is in W to the 1P sub 0 because the root convergence of the gradients and the strong convergence of the functions.
Okay, the last part is showing that U is actually a weak solution.
They do this by taking an arbitrary test function CSI in W to the 1P sub 0 and looking at the limit of the integral equation satisfied by U sub M as M goes to infinity.
They use the structure lemmas, condition 7, and the weak convergence of U sub M to U's.
And the strong convergence of U sub M to U in L to the P.
They might also use an auxiliary sequence, V sub M, that converges strongly to U in W to the 1P sub 0 to help with the limit.
Eventually, they show that U satisfies the weak formulation, so it's a weak solution.
Okay, and corollary 5.6 extends this to non-zero boundary values.
If we have a boundary value G in W to the 1P, they show there's a weak solution U where U minus G is in W to the 1P sub 0.
They do this by defining W equals U minus G, which has 0 boundary value.
And substituting that into the p-Laplace equation to get a modified equation for W.
They then get energy estimates for W and use a similar finite dimensional approximation argument.
And finally show that the limit of the approximate solutions is a one solution to the modified equation, which means U is a weak solution to the original equation with the boundary value G.
Okay, so that's existence and uniqueness.
Now let's talk about regularity in section 6.
Page 12.
They want to know how smooth the solutions are.
Theorem 6.1 is the main regularity result.
If the coefficient A is an E of omega and is Holder continuous with exponent alpha over P prime, where alpha is between 0 and 1, and P prime is the Holder conjugate of P.
And if the source term F is also Holder continuous with the same exponent. All right, welcome to another deep dive today. We are going deep into some pretty advanced math.
Yeah.
And today we're aiming for a little bit of a shortcut. We want to give you the core insights of some very complex research. So no need to wade through every single detail of, a pretty hefty paper yourself. I think today we're really focusing on the math, the equations, the proofs.
Yeah. Definitely not a casual overview today. We're going pretty deep into, some very specialized stuff. But we know you guys listening are pretty solid in your math background, so we're not going to shy away from the technical stuff.
Yeah, let's embrace the technical.
Yeah.
Excited for this one. So the paper we are looking at today, it's called Existence, Uniqueness, and Regularity for Elliptic p-Laplace Systems with Complex Coefficients. Now, that's a mouthful. It's by Wontae Kim and Matthias Vestberg. And it's a pretty substantial piece of work. So we're here to kind of, guide you through it.
Yeah, absolutely. So we are going to explore several themes that are directly addressed in the paper. So first, we're going to take a look at how the theory surrounding real-valued p-Laplace equations and how that is extended to the more complex landscape of complex valued functions.
Sounds complicated already.
It is. It is. It is. And the modifications that are required, they're pretty insightful. So definitely worth taking a look at.
Yeah. And once we've gotten past that first step, I guess what comes next?
Well, then we're going to examine the precise conditions under which we can guarantee the existence of solutions to the Dirichlet problem for these complex systems. And we're going to look at, when those solutions are unique.
Got it.
So the interplay between the real and the imaginary components here is going to be really, really important.
Okay. And then?
Then we turn our attention to the proof of the Schotter estimates.
So what now?
The Schotter estimates. Yeah, these estimates are super important because they help us understand the regularity of these solutions, the smoothness, and we're going to see how the Holder continuity of the coefficients in the source terms influence how smooth the solutions are.
Sounds good. So we talked about the real value to complex value, and then the existence and uniqueness. We're talking about the smoothness now. What's the final thing we're going to hit?
Okay, so finally, we're going to look at how these solutions behave. When the coefficients themselves are not fixed, but actually depend on a complex parameter.
Okay.
And this leads to a result. That concerns the differentiability of the solution map with respect to this parameter. And this is a concept with pretty significant implications.
I bet. So as complicated as this all sounds, I guess, it's important to remember that it's not purely abstract.
Right.
There are applications for this stuff.
Exactly. So as the authors of the paper hint at studying these complex p-Laplace systems, it's not purely theoretical. It actually connects to various branches of mathematics. And it holds promise for applications in fields like depot nets. Now, these are a novel type of neural network that are designed to learn operators. So while, yes, the math we're going to be discussing is advanced, it's driven by important questions and potentially has some real-world impact.
Okay. Well, now that we have a general overview, I guess, let's jump right in. So page 1 of the paper, the introduction.
All right, so this is where we're introduced to the central equation that the authors are going to be studying.
Okay, hit me with it.
All right, so it's a dφ plus OP22 d plus 2 plus EP2 plus EV. Now, this should look somewhat familiar to those of you familiar with the classical p-Laplace equation. It's got a similar structure, but the key difference here is that the coefficient a and the solution u, they can take complex values.
Okay, so right off the bat, it's a little bit different than what we're used to.
Yeah, and this is a big departure from that real valued theory.
Got it. So let's break down the pieces here. So we've got the parameter p, which is a real number, and it's between 1 and infinity. So AB, and this exponent governs the nonlinearity of the equation.
Exactly.
We've also got AP that's non-negative.
Yeah.
And it's between 0 and 1, so IP001. Now, this A term, it often shows up in regularization techniques.
Right. And a lot of the results in the paper, they actually hold true, even if A is 0.
Okay.
Which corresponds to the standard p-Laplace operator.
All right. Makes sense. Then we've got A, which is our domain.
That's right.
It's an open and bounded subset of n-dimensional real space.
Yep.
And here n is at least 2.
At least 2.
Okay. And the coefficient function, it's denoted by a, and it maps from our domain A into the complex numbers.
Sure.
Right. See, and this complex nature of A, this is a big focus of the paper.
Yeah.
Right? And then we've got A, the solution we're looking for, and it's a function that maps from A into co. So it's a vector of n complex numbers, where n is a positive integer greater than or equal to 1.
Right.
And finally, we've got F. That's our source term. And that maps from A into Q. So basically a collection of n by n complex matrices.
That's right.
Okay, so that was a lot to unpack. But I think I got it. Anything else to add there?
Yeah, it's important to note that most of the results, they hold true even when A is equal to 0.
Okay.
The key exception to this is the differentiability result, which is addressed later on in the paper.
Right.
And that one needs to be greater than 0.
Okay, so that differentiability result is a little different than the others.
Yeah. You can kind of think of A as like introducing a small bit of smoothness,
right,
or non-degeneracy into the operator.
Okay, that makes sense.
Right.
So since we're working with complex valued solutions for it, we can't use that standard real inner product.
That's right.
That we normally use for these problems. Instead, we've got to use its complex counterpart.
Right.
Which is denoted by A.
Yep, exactly. And this complex inner product, it accounts for both the real and the imaginary parts of the vectors.
Okay.
And it's fundamental to this analysis.
All right. So we'll see that again.
Oh, you'll be seeing that all over the place.
Yeah.
We're actually going to define it very precisely in definition 2.2.
Okay, we'll get there. But it's good to keep that in mind.
Definitely, definitely.
All right. So the source term f, they're using, I guess, a pretty standard integrability condition.
Right. So they assume that f belongs to the Lebesgue space, L super O,
Okay.
where p is the Holder conjugate of p, and that's defined by 1 over p plus 1 over p equals 1.
Okay, so pretty common condition.
Yeah, this just makes sure that the integral pairings in the weak formulation of the problem are well-defined and finite.
Right. So now let's get into the complex coefficient, x.
All right, so this is where the novelty and the complexity of this whole problem really comes in.
Okay, so buckle up, everybody.
Yeah, buckle up. So they break down ax into its real and imaginary parts. Like this, ax equals a sub s sub x plus I sub s x, where both a sub s and a sub is x, they're real valued and measurable functions on our domain A.
Got it. So this lets us look at the influence of the real and imaginary parts, both separately and together.
Exactly. Now, when we talk about ellipticity, which is really important to make sure the problem is well posed,
Right.
we have to consider both a sub I sub x and a sub x. Now, they introduce specific conditions for this.
Yip me.
Okay, so they say there's these positive constants, E and L, where 0 is less than E, which is less than L, which is less than infinity.
Okay, so 0 less than L less than infinity.
That's it. And for almost every x in A, these inequalities have to hold. A sub x and a sub x plus a sub x.
Okay, so these conditions are super important, right?
Absolutely. Now, it's important to note that the imaginary part, S sub x, can actually be negative.
Okay.
So using its absolute value in these conditions, it's essential.
Right, because it could throw things off otherwise.
Exactly. And these conditions, they have implications for the operator itself. Essentially, they make sure that the real part kind of dominates in a certain sense, providing some stability.
Right.
Make sure that the operator is what we call coercive.
Okay.
And L keeps it from becoming degenerate. This is a really key insight into what makes these systems work.
So let's just start looking for the solutions.
And exactly. Now, because of these ellipticity conditions, the operator has some important properties. We've got something called a structure bound.
Okay, what's that?
It's basically this. Ax, 2 sub s, 2 sub sub sub, 2 sub sub, 2 sub sub L. Right.
Representing a gradient.
That's it. And this bound, it's important because it tells us that the operator doesn't grow too fast as that gradient increases.
Okay, and that's important. Why?
Well, it helps us prove that the solutions or approximations of solutions are bounded.
Gotcha. And we also have a coercivity property.
Yes. Now, coercivity, it's a fundamental property in partial differential equations.
Okay.
It basically gives us a lower bound on an energy functional that's associated with the problem.
Okay.
And it often helps us prove the existence of solutions.
Using what?
Using things like variational methods or monotone operator theory.
Right. So what's the actual equation for this coercivity property?
All right, so it's re-x-eps a piece, a substeps, 2x p, 2 substeps, 2 substep.
Makes sense. Now, you mentioned monotonicity earlier.
Right, monotonicity. It's really important for proving both the existence and the uniqueness of solutions.
For a lot of these nonlinear PDEs.
For a lot of them, yeah. But in this complex setting, it gets a bit more complicated.
How so?
Well, the monotonicity of this operator, it depends heavily on the relationship between the real part, a sub-sub, and the imaginary part, a sub-sub of the coefficient.
Oh, interesting.
And to make sure we have monotonicity, we need an extra condition. It's C as sub x.
Okay, and C and S are positive constants.
Yeah. We'll see those later in lemma 4.2 and 4.3. They're part of the structure lemmas.
Okay, and C is the lower bound.
From the ellipticity condition, right?
Right, so this new condition, what's it doing?
Basically, it puts a limit on how big the imaginary part can be compared to the real part.
Make sure the real part stays in control.
Exactly.
Okay, so it's all about this balance.
It is, and under these conditions, the authors are able to prove that a weak solution exists.
Okay.
And they do this by extending that monotone operator theory from the real world to this complex world.
Very cool.
It's pretty cool. And they mention that this is a new contribution to the field.
Wow.
So the fact that existence relies on this balance between the real and the imaginary parts is really important.
It tells us that structure is key, right?
Exactly.
Oh, right.
It's what determines whether or not a solution can even exist.
That's huge.
Yeah.
So besides existence, the paper also talks about uniqueness, right?
Yes, yes. And this uniqueness, it comes directly from an energy estimate.
Oh, okay. So what are those?
Energy estimates, there are these inequalities that put bounds on the solutions,
Yeah.
and they help us prove uniqueness
Mm-hmm.
by showing that if we have two solutions, the difference between them has zero energy.
Meaning they're the same.
Exactly. And it's important to know that the solution we find is the only one.
Got it. So the introduction also gives an overview of their work on regularity, right?
Right, right.
Like how smooth are these solutions?
Exactly, exactly. And they're able to get the classic Schotter estimate.
And remind me what that is.
Sure. So Schotter estimates, they're basically bounds on the Holder norm of the second derivatives of the solution.
Okay.
Or sometimes it's gradient in terms of the Holder norm of the right-hand side of the equation
Right.
and the coefficients. Now, Holder continuity, it measures how smooth a function is. So getting these estimates for Holder continuous coefficients A and source term F is a big deal.
Yeah.
It tells us how smooth the solutions are.
Got it. So finally, the introduction sets us up for how depends on a complex parameter.
That's right, that's right. They mention a differentiability result for the map that takes this parameter to the solution.
Wow.
And this is looked at along line segments within a domain of the complex parameter, specifically for A greater than 0 and for rectangular domains.
All right. So this is important for understanding how sensitive the solutions are to changes in the parameter.
Exactly. And they even make a connection back to the linear case, where P equals 2.
Okay.
Now, in that setting, questions about complex differentiability have been studied a lot, particularly for series expansions of solutions with respect to parameters,
Yeah.
and they apply to things like depot nets.
Right. So this just shows how relevant their work is.
Absolutely. It's not just some niche mathematical thing. It has broader implications.
I like it. Okay, so that gives us a good overview of the problem and the results.
Yeah.
Now let's dive into the preliminary definitions in section 2.
Okay, so these definitions, they start on page 2. They're super important.
Now to get the basics down, right?
Yeah, exactly. Without these, understanding the later stuff is, well, pretty much impossible.
Agreed. So definition 2.1 starts off by defining the real vector space Rio.
Right. And an element F in this space, you can think of it as an n tuple of vectors in row.
Got it. And then they define the inner product, right?
Yeah. So if we have two elements, F and G, in Rolo, their inner product is F G sub 5(1), F sub S sub.
And the dot on the right-hand side, that's just the regular dot product in row.
Yep.
Okay, and then we have the norm, sub through sub, which is just the square root of the inner product of F with itself.
That's it.
So for a proof sub, that's F sub 12 sub.
Right. Which just measures the magnitude of F.
In this multi-vector space.
Yeah.
Okay, so definition 2.2, I guess this extends those ideas to the complex world.
Yeah, to co.
So an element F in co, it has a real part, F sub sub, and an imaginary part, F sub sub.
Right.
And both of those are elements of RAM.
Right.
So F sub sub plus I F sub sub.
That's it. And multiplying by a real number is pretty straightforward, too.
Like CF sub a sub plus I CF sub sub.
Exactly.
Okay, so definition 2.2 also introduces the complex inner product.
Right. And this is a really key definition.
Give it to me.
All right. So for F and G and co, their inner product is F sub J sub O sub right sub 1 and sub plus F sub A sub test sub B sub E sub sub plus F sub a sub plus F sub A sub plus F sub A sub G sub D sub.
Okay, that looks a little intimidating.
It's not as bad as it looks. So we sum over the n components, and for each component J, we have a term with the dot product of the real parts and the dot product of the imaginary parts.
So that's F sub Z sub G O sub U sub and F sub B sub G U sub sub.
Yeah, and these give us the real part of the complex inner product.
Okay, and the imaginary part comes from the term E sub, D sub E sub plus E sub E sub E sub.
That's it. So it combines the real part of one with the imaginary part of the other.
Right. So it's kind of like a more nuanced way of measuring how complex vectors relate to each other.
Exactly.
Got it. So then we have the norm of an element F in co. That's F sub to sub.
Right. And that's defined as hub sub sub, X sub 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 plus F sub 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 up sub 12.
So we're using the norms of the real and imaginary parts here.
Yeah, it's basically the square root of the sum of their squared norms in Royal.
So it's measuring the magnitude of the whole complex element f.
Exactly, exactly. Now, definition 2.3, this one's pretty neat. They introduce this notation f, which we read as double f.
Okay.
It's a vector in Rojo, and it's formed by stacking the real and imaginary parts of the n vector components.
Okay, walk me through that.
Okay, so if we have f sub r 1 sub, f sub r n sub, f sub e 1 sub, f sub n sub. Basically, we take our complex vector of dimension n and we turn it into a real vector of dimension 2n.
By stacking the real imaginary parts.
Exactly.
Got it. And then there's qf. It's kind of similar, right?
Yeah, qf, f sub n sub, f sub r1 sub, f sub r1 sub, f sub r1 sub. There's some rearranging and sign changes going on.
It seems random, but I'm sure there's a reason.
There is. So they've introduced these notations, f and qf.
Right.
And these let us take our complex problem and move it into a real space.
Oh, okay.
Which can sometimes be easier to work with.
Makes sense. So the key takeaway here is that we can use what we know about real inner products when dealing with these complex quantities.
Exactly.
And that's thanks to the relationship that definition 2.3 establishes.
Right. It says that FG plus IF2G. So the dot on the right-hand side, that's the regular dot product in our array.
Okay, so we can take advantage of those properties.
Absolutely.
Very cool. And we also have a norm equivalence here.
Yep. It's F sub F sub Subaru, F sub Rudu.
Okay, so the norm of F and co is the same as the norm of its representations in the real space.
That's it. This equivalence is going to be used a lot throughout the paper.
Right. It bridges that gap between the complex and real settings.
Right. Exactly.
Okay. Definition 2.4. This one seems pretty straightforward.
Yeah, this one's easy. It's just dealing with the case where f is a scalar, so FC.
Okay.
And it defines the real and imaginary parts of f.
Like re-f and inf.
Exactly. Just like you'd expect.
All right. Makes sense. So definition 2.5 is a reminder of the Lebesgue space.
That's right. L sub super.
So this is the space where the source term usually hangs out in real-valued p-Laplace problems.
Yeah, it's the space of all measurable maps f from f into rho such that the integral of the pth power of the norm of f over a is finite.
Right.
Okay.
Wow.
Now, definition 2.6 brings us to Sobolev spaces.
Okay. So we're extending that familiar what you suppose subspace to the complex world, right?
Exactly. To WSUP 1 sub.
And a function is in this space if both u and its gradient have finite L sub norms over A.
That's right. And we split it into its real and imaginary parts.
So u sub plus u sub.
Yeah. And both u sub and u sub have to belong to the regular real Sobolev space.
Would sub 1 sub.
Exactly. And the gradient of u is defined component-wise.
So u sub plus I sub e sub.
That's it. The gradient acts separately on the real and imaginary parts.
And that subscript 0 in u sub means we have 0 boundary values.
In a weak sense, yeah. And this is the space we use for Dirichlet boundary value problem.
Got it. So last but not least, definition 2.7.
All right. So this one gives us some handy notation.
I'm all for handy notation.
Yeah. So for and with sub, they define u as a vector in a real space by stacking the real and imaginary components of u.
Okay, so if u sub where each u sub u sub r sub plus e sub b sub.
Right.
And sub do have 1 sub u sub I 1 sub, u sub o feka, u sub n sub.
Exactly. And then rs is just the gradient applied to each component of u.
Right. And then there's q
chuch. Just like qf and chuch. So q. U sub I 1 sub, U sub bar sub, U sub r sub, and su sub r n sub, E sub b bar sub, and su r n sub.
All right, so all these definitions, they're going to make things a lot easier later on.
Definitely.
Okay.
It's going to make the expressions and the proofs much more manageable.
Great. So now we're ready to move on to section 3.
Okay, so section 3 starts on page 4. And this is where we really get into that complex valued p-Laplace system.
All right, let's do it.
Okay. So they start off by reminding us about that complex coefficient A, right? Which is ax a sub x plus a sub x.
And a sub and a sub are bounded and measurable.
Right. Exactly. And then they bring back those super important ellipticity conditions.
Okay.
They're labeled as 5 in the paper. A sub x and a sub plus a sub is LL, and this is for almost every x in.
Right. And
All right.
and L are those positive constants.
That's right.
So we've got to keep stressing how important these conditions are.
Absolutely. Absolutely. It all comes back to these.
They're the key to making this all work.
Yeah, they're like a generalization of the standard ellipticity condition.
Right, when we're working with real coefficients.
Exactly. But here we have to account for the complex part.
Makes sense, makes sense. So definition 3.1.
All right, so this is where they define what it means to be a weak solution.
Okay.
So we're talking about a function belonging to the Sobolev space we sof 1 SOP-FM,
Right.
and it's a weak solution to a df plus df pu so. The key here is that we reformulate the differential equation into an integral.
So for every test function in Wigsobo sub dxx,
Right, that's the Sobolev space with 0 boundary values.
we have this equation. Isubasub of Potcast, these sub dx eats up to the
That's it. And this weak formulation, it's pretty common in PDEs.
Especially when we're looking for solutions that aren't necessarily differentiable in the classical sense.
Exactly. Instead of the equation holding at every point, we just need it to hold in an integrated sense.
Right, against these test functions.
Right. And using WSUP1 sub makes sense because we're usually dealing with Dirichlet boundary conditions.
Okay. And that inner product, sure.
Yeah, that's the one we saw in definition 2.2.
Right, right.
Yeah.
Okay, so now that we've got all the definitions in the mate equation, let's move on to section 4.
All right, so section 4 is all about structure lemmas.
Structure lemmas.
Yeah, they're not really results in themselves, but they're these inequalities and properties.
That we get from the assumptions we've made.
Exactly, like the assumptions about AX.
Right, and all those norms and inner products.
Right, right.
So these are kind of like the building blocks for the proofs later on.
Yeah, they give us the tools we need to work with these expressions.
Okay, so let's go through them. Lemma 4.1.
All right, so this one gives us an expansion of f plus d2 plus g, the two, so g, g, f, j.
Yeah. And it's expressed in terms of fg, qf, and qg.
That's right. Those are the real space representations of f and g.
Right, right.
And it uses the regular real inner product in other world.
So it helps us connect back to the real world.
Exactly. And that connection is super important for this whole analysis.
Okay, I'm seeing the pattern here. Lemma 4.2.
All right, so this is a coercivity condition.
But specifically for the real part of an expression.
Yeah. So it says there's this constant c, which might depend on p.
Right.
Such that next plus f plus g, 2 sup f a 2 sup plus g f g.
Okay, and the dot product on the right-hand side is an LOR.
Right. And this inequality is important because it gives us a lower bound.
And it's related to the difference between f and g.
Exactly.
And this helps with uniqueness and convergence of iterative schemes.
Exactly, exactly. Now, lemma 4.3 puts a bound on the difference of the operators.
Okay.
So there's another constant c's, which might depend on p again.
Right.
Such that plus f plus g plus f plus g plus g plus 2 plus g plus g plus g plus